Hello, welcome to this lesson. It's from the radioactivity topic, and we are covering an important one for this topic here, types of radiation. Okay, we're going to start this one off with a confused.com session. I'm going to introduce some characters, and they've all got questions regarding types of radiation. So let's see what we've got out there. So this individual is wondering what ionizing radiation is. Well, mate, we're going to cover all of that in this lesson, so please stick with us. What are you thinking, pal? I'll tell you what, we'll just ignore that one, shall we? Right, oh dear, what's this guy thinking? Will my nuclear bunker protect me from all types of radiation? We'll definitely answer that one for you, mate, in this one. Clearly pay you a lot, starring in the old Muppet films there. We'll find out. Yes, indeed. Cue him, innit? I remember something about ions from chemistry lessons. Well done, lad. Brilliant stuff. We'll certainly mention ions from chemistry lessons, and there is a lot of overlap in terms of when we're thinking about ions in physics as well. Wonder what he's thinking about. Alpha particles, will they improve the flavour of my cheese on toast? I've heard they have lots of energy. He's about 70 or 80 years behind in his information he's got in his head there. Clearly, alpha particles you would definitely not want sprinkling on your toast. And finally, all right, Bart, how's it going? Nah, well, never mind. Stick with us. You never know. We might possibly be able to help you understand a little bit on this one. So, types of radiation, here we go. Right, objectives very quickly. The first one, and again, I can't stress enough on this, you need to know it for chemistry, you need to know it for physics. You must be able to recall the mass and charge for protons, neutrons, and electrons. First objective. Second one, we need to then link that to alpha, beta, and gamma radiation. And again, we need to be able to link the mass and charge of protons, neutrons, and electrons to those types of radiation, alpha, beta, and gamma. They're the three we're looking at today, and compare the penetrating and ionizing abilities of alpha, beta, and gamma radiation. If you're not clear on what those words mean, we will definitely clear them all up by the end of this lesson, so stick with us. I'm afraid this is one of them moments where a teacher just says, copy the information in the table and learn it. It's a buy one, get one free deal, this one, isn't it? You need to know it for chemistry, you need to know it for physics. So please make a note of that table and then please spend about 3 or 4 minutes drumming it into your head. It's not difficult to remember. Again, I'll be honest, I get depressed every year by the amount of students that can't recall those basic facts. Please do not be one of them. Right, so hopefully you should have written that table down, you should have paused the video, and you should have been spending the last 3 or 4 minutes drumming that into your head. If you've not, please stop, and please make sure you've done so, because you can't do quick draw unless you've memorised those key facts from that previous table. So what on earth is quick draw, Mr. Firth? Well, how quick on the draw can you be? On the next slide, I'm going to rapidly put up questions relating to the previous table. How quick can you answer them? Right then, are you ready to play quick draw, folks? Here we go. I'll start off slow, but it's gonna get fast. Let's be quick on the draw. I didn't really give you too much chance on the last one there. Have a go back, have a go again. If you didn't get them all right straight away. But again, I will stress, you really do have to know those facts. Okay, so you've seen that diagram on an earlier slide. It is, of course, an atom. Question is, how can you tell from that diagram which atom it is? You should be able to. If we're clear that the two red circles in the middle there are protons, that gives us the atomic number. You're still not clear if I say squeaky voice. I'm sure you will be. It is, of course, helium. So as I've mentioned there, the atomic number, and again, I'm just highlighting that there, is 2. And that refers to the 2 protons in the nucleus. The mass number, of course, of helium is 4. And again, why is it 4? Because in the nucleus, there are 2 protons, 2 neutrons. Add them all up, and you get a total of 4. What would it be like if you took away its electrons? Well, at the minute, it's got electrons, it's a neutral helium atom. don't forget the two positive protons in the nucleus balance out the two negative electrons that are orbiting it. If you took away those two electrons, it would now be an ion, because it's an atom that's gained or lost electrons, and therefore it's become an ion. In this case, it would be positive, wouldn't it? So what I want you to do now is match up the information in the boxes that I'm about to click up. There they go. And I want you to put them into the table for the three types of radiation. Now, you're going to need those diagrams to help you with that. It should be clear what those diagrams represent from what we've done so far. And what I want you to do is put that information in. So at this point, you need to freeze the video and you need to draw that table out, fill the information in, because I'm going to give you a countdown, and then I'm going to talk you through the answers. So 3, 2, and 1. Okay, answers coming up. So we'll do the descriptions first. The first one, it's the helium nucleus, as we've mentioned, and again, it's made up of 2 protons, 2 neutrons, 2 reds, 2 greens. Again, I'll just stress, red is usually what we use to represent protons, and the green there would represent the neutrons. The description of the electron, well, it's an electron, isn't it, really? But again, we refer to that, it's got a slightly different name in terms of when we're referring to it as a type of radiation. The bottom one, it's not actually a particle. It's very important that. It's an electromagnetic wave. You've come across those in the topics on electromagnetic radiation that we thought about earlier on in terms of the parts of the electromagnetic spectrum. So they should be familiar to you. So the mass of the helium nucleus has to be 4, because it's got 2 protons, 2 neutrons. Add them all up, it gets to 4. And the mass of the electron is almost 0. Don't forget also that because that electromagnetic wave is not a particle, it also must have a mass of 0. Okay, and then to clear up the charges, well, clearly the alpha particle's got 2 protons, so it's got a +2 charge. Be careful on that. Don't say it's positive. Say it's positive by 2, +2. The electron, again, -1. And for the charge of the electromagnetic wave is 0, because again, it's not a particle, so therefore it can't carry a charge. Now, in terms of the names of them, the top one, the helium nucleus, that is our alpha radiation. The electron is actually referred to as beta radiation, or more specifically, it should be beta minus there. So actually, I'm just going to add that one in. You'd normally see a little minus signal associated with that beta minus particle. And then finally, we've got the electromagnetic wave, which represents gamma radiation. And again, that squiggly Y is the symbol for gamma radiation. I'll say this one more time, like the table from the start. It's very important, that information there. Please make sure that you learn it. Right, again, cover your table up. And just to check that you can remember them, again, there are some types of radiation. There's a couple of other ones there as well. You've got neutron and positron in that list. Neutrons you're already aware of, so should be no problem. Positrons, I'll say no more. By a process of elimination, you should be able to work which one that is. So if you want to have a go at them, I'll click up the answers in 3, 2, and 1. So our alpha particle, again, it's our helium nucleus. Again, the description we've already got. The beta particle, again, because it's a high energy electron, again, we've got the symbol E there. Now, the 0 at the top represents the fact that it's almost 0 in its mass. And the -1 that you can see underneath that, again, is representing the fact that it's got a -1 charge. Now, next one, again, we've got the positron. Now, the positron we need to know about in the next lesson on radioactive decay. So we're kind of introducing it today. Hi, positron, how are you doing? So the positron is exactly the same as an electron, but as you'll notice here, it's got a +1 charge. So I'm sorry to throw even more subatomic particles at you, boys and girls. Believe me, there are a hell of a lot out there. Think yourself lucky, actually, we only need to think about 4. So we've also got gamma there, and again, high frequency electromagnetic waves, and neutrons, again, clearly, they are neutral charge with a mass of 1. And again, we need to know about neutrons being emitted when we think about radioactive decay in the next lesson. So again, hopefully that's helped to drum it in. But I stress you need to know the definitions of those. Rather a nice clip here, I think. And again, it can clearly help us to understand the charges associated with the types of radiation. So have a look at the picture. What it represents is a source of a radioactive material that's decaying, and it's emitting the types of radiation, all of them. And they are being emitted through an electric field. Now, that's represented by the plus, the negative and the positive electrode there, and the lines are showing the electric field between them. Have a look and think. I'll shut up and I'll share my thoughts with you in a little while. Right then, hopefully you're okay with this idea. The alpha particles are positively charged, and so they are attracted to the negative electrode. Opposites attract. Same for the minus or the negative electrons, the beta minus particles. They are attracted to the positive electrode. The gamma and the neutron, again, they are not affected by the electric field because they are both neutral in charge. I'll leave you with one more question. Why are the beta minus particles being deflected more than the alpha particles? As they would have said once upon a time, answers on a postcard or an email, but the first person that can get that answer to me, I will find some way of praising you greatly. So have a think about that. Why are the beta minus particles being deflected more than the alpha particles? Right, we're on to the final objective here. So we've covered about subatomic particles. Hopefully you're clear on the properties of the types of radiation. So now we need to think about their ability to penetrate through things and also their ability to ionize other atoms. So here we go. I'm going to talk you through this clip. It's quite a nice one to show the penetrating ability of the 3 types of radiation. Again, their ability to pass through other materials. Here we go. So we've got the beta minus particles represented by the yellow circles. We've got the gamma rays as the blue rays there, obviously. Now you'll notice very clearly there, we can infer something about the speed of the alpha particles because they're still coming through and one is just about reaching us now. So straight away, we can say something. The electrons are almost traveling at the speed of like the gamma ray. Alpha particles slower. Now, what that represents, a piece of paper has been dropped in. And straight away, you'll notice that the alpha particles, they can't get through a sheet of paper. Aluminium goes in. And we will notice that that has now stopped the beta minus particles, the electrons, but the gamma still clearly gets through that. Now, massive big chunk of lead here, and we'll notice that has stopped most, but not all of the gamma radiation. So even a really thick piece of lead, some of that gamma, because it's such a high energy electromagnetic wave, it literally just will whiz through the empty space of most of the atoms that it passes through. Right, this slide follows on nicely from the last one. All I want you to do is make a note of the information. You can see there the 3 types of ionizing radiation as it progresses, this animation, and you can see their ability to penetrate those different materials. Examiners are dead keen on this one, so please make sure that you've got that information down before you move on. The extension we'll mention a little bit later on in this lesson as to why each one penetrates as far as it does. Same process again here, folks, really. Top diagram is just another representation of the previous 2 things that you've seen. The diagram underneath links it to obviously this idea of dangers of ionizing radiation to the human body. So again, an extension question there linking it. Why would you not want to breathe in alpha particles? Have a think. We'll link that in when we think through a little bit later on in this lesson. So have a look. You might want to freeze it, make a note, before you move on. Okay, so well done. You've made it to the final part of the final objective. Let's just recall this thing first of all. Atoms of an element contain equal numbers of protons and electrons, so therefore they are neutral. Ionizing radiation that we're thinking about, alpha, beta, and gamma, can alter that neutrality. And they alter it by removing electrons from their orbits. Now, could I stress here at this point, when I say orbits around the atom's nucleus, it's the outer electrons. Now, you should be familiar enough with atomic structure by now. Some of the electrons are further away from the nucleus. Don't forget the nucleus has a positive charge, and those electrons that are further away are less strongly attracted. So it's those that are more easily taken away, if you like, from the atom by ionizing radiation. Don't forget, an ion is an atom that has gained or lost electrons. If an atom loses an electron, it becomes I'm sure you got that, a positive ion. Now, your chemistry teachers will be talking to you about ionic bonding, and you'd be thinking about non-metals like chlorine gaining electrons to become a negative chloride ion, and also things like sodium becoming a positive ion because it's lost an electron. Of course, it's a metal element. They form positive ions, and that, of course, would result in ionic bonding to form sodium chloride. But we're not looking at it from that point in terms of the physics. When we're talking about ionization, it's about removing electrons, so we're always referring to a positive ion being formed. Now, I'm going to show you 3 diagrams. And as it's saying there, I want you to describe the types of radiation, how it affects the atoms they come close to. Hint there as well, think about it. Here are the diagrams. There's our alpha radiation affecting an atom, beta affecting an atom, and slightly different format, I'm afraid, but that's showing gamma radiation affecting an atom. Why is the alpha particle more ionizing than the beta? Why is gamma the least ionizing? I'm going to shut up for about a minute, and I want you to look at those diagrams, see what you think, and then I'll share my thoughts at the end. We'll summarize it on the next slide, but I want you to think about it first. Off you go. All right, hopefully you sat there and you've had a good look at them. I'll just talk you through it in terms of each one. Now, we'll deal with the alpha first. Now, again, alpha particles are emitted from radioactive sources at high speed. They've got a high mass and charge. We know about that one. So therefore, they can ionize more atoms that they come close to. Now, the negative outer electrons, don't forget, they're attracted to the positive alpha particle. Now, every time the alpha particle ionizes an atom, it's going to lose some of its energy. And because alpha particles ionize more atoms, they lose energy more quickly. And that's why they are very weakly penetrating. You can't get through paper, you can't get through skin. Now, as that loses energy, the alpha particle will eventually attract 2 electrons, and then it'll just be a helium atom. Could I just quickly link this one to the extension on the previous slide? You don't want alpha particles inside you. If you've got something radioactive inside your body, I don't know, for example, radon gas, you breathed it in, it decays by alpha decay. and that's emitting alpha particles, which are highly ionizing inside your body. That's dangerous. If those alpha particles were emitted onto the surface of your skin, you're relatively safe because alpha can't even get through paper. So that was your alpha. Beta, now because it's got a lower mass, because it's got a lower charge, it's less ionizing, a lot less. Now a fast-moving beta particle, it's got to come close to the outer electrons to be able to remove it from the atom. And again, because it's small and because the electrons are small, there's less chance of that encounter happening. So your beta particles will penetrate further before they cause that ionization. Now gamma, again, if we look at that one, it's got no mass, it's got no charge. It moves at the speed of light, so it's going to pass through most of the empty space of every atom that it encounters. Now, if, as that diagram shows, it does pass on some energy to an atom, and that energy is enough, it can cause an outer electron to be lost from that atom. So again, it will form a positive ion. Okay, I've covered a lot there, and again, hopefully you followed it through, and hopefully I've explained it clearly. As I said, I'm going to click on in a second, and the next slide will hopefully get you to get it down a little bit more clearly. Right, we can quickly summarize the previous information. 3 key paragraphs here. Your job clearly is to fit those words into the gaps. I'll give you the countdown and I'll click up the answers. So here we go. If you want to freeze the screen, 3, 2, and 1. Okay, how'd you get on with them? Hopefully straightforward enough. As I said, that summarizes the key points there, and hopefully helps to finalize or sort things out in your head and make it a little bit clearer for you. Okay, this is the and finally section. I'd just like to say thank you for getting through till the end on this one. Hopefully it's helped you a little bit. Nice image coming up here. And what we can see is a star being dragged into a black hole. And as it disappears over the event horizon, we can see a burst of gamma rays. And if one of them was pointed at the planet Earth, it would make the recent pandemic seem like a picnic in the park. So let's be grateful for that one. We haven't been exposed to a burst of gamma rays from a distant black hole consuming a star. Reasons to be cheerful, folks. I'll be following this up very shortly with a lesson on radioactive decay and then another one on half-life as well. So keep your eyes out for them. Hopefully I'll better clear a little bit up on those for you as well.